and welcome to another seminar, Thursday seminar in computer engineering. And today, I hope you are noticing something different in my background. It's not the AI or the computer graphics fake backgrounds. This is live from our Smartness Engineering Research Center Fresh Lab. And right now over 5G standalone connectivity that we have started finally. So hopefully our network and our telco cloud, because there is some cloud in the management system of this private network that is running the show today. And that's precisely the topic of today's seminar, 5 key pillars of telco cloud evolution by Paul Veitch, directly from British Telecom, right? Paul, we talked last time in NetSoft in Budapest and invited you, and thank you for your time, for your contribution. As usual, our seminar speakers have a long biography that I don't read. Paul, if you want to introduce yourself, feel free. And I'm looking forward for our conversation in around 40-45 minutes. I will be seeing which questions our students have prepared, and also if anyone live wants to get some question to you, I will do my best, leave it over the chat. Paul, I will stop sharing my screen right now. Thank you again. Let's now you move to you. You can start your screen sharing.
Okay, thanks, Christian. I guess I better just check you can see the slides.
Yes, perfect, excellent.
Okay, okay, I'll kick off then.
Yeah.
Thank you very much. Yeah, thanks, Christian, for the invitation to give this talk. Yeah, I won't give my life story to save time. But yeah, my name's Paul Veitch. I lead the Cloud Infrastructure Research Centre of Excellence, based at British Telecom's R&D labs in the UK. I actually hail from near Glasgow in Scotland, but I've lived for some time in Suffolk in the UK, and that's where BT's R&D labs are. I'm also a BT Distinguished Engineer. That's a polite way of saying I've worked here quite a long time and worked on a range of different things. Okay, so what can we expect from this talk? So I've divided it into 3 main segments. The first segment is fairly short, but it's a bit of a scene setter. I'm just going to explain a little bit about telco cloud. What is it? How did we arrive at this concept called telco cloud? And position how it is evolving. And then we get into the meat of the talk, where I really talk about what are the 5 main pillars that are driving telco cloud evolution. I'm not going to go too deep in any one of those 5 things. I'll really be focusing on why they matter to a telco, for example, and what are the key considerations. So that will be the meat of the presentation, and then some concluding remarks at the end. Okay, what exactly do we mean by telco cloud? Telco cloud, I would say, doesn't have a definitive meaning as such, but there's a general consensus what we mean when we talk about telco cloud. I really like this definition. I'm not going to read it out word by word, but this comes from an article by STL Partners. They're a consultancy based in the UK. I think they just encapsulate what telco cloud is pretty well. The 2 bits that are highlighted in blue in that paragraph, I think are the important ones. It talks on the one hand about actual infrastructure virtualized and programmable infrastructure, and the fact that that leverages things like NFV and SDN, network function virtualization, software-defined networking. And I kind of think of that, if you like, as the what is it we're doing. The other part of the definition here, though, talks about cloud business practices, and how these two things, the what's, if you like, and then we think of these as the hows, actually marry together in what we call telco cloud. And it's a bit of a busy slide, this. I'm not going to step through every bit of this. There's the graphic on the right and the salient points that are sort of setting the scene here on the left-hand side of the slide. So that definition of telco cloud, I think what it does is it helps inform how we've arrived at current deployments of telco cloud, and actually the fact that they had their origins, if you like, in the concepts of NFV and SDN. NFV and SDN, you guys will probably know, kind of burst on the scene more than 10 years ago, 2012, 2013. The graphic on the right is kind of showing how we've evolved from maybe quite early deployments and implementations of, when I talk about NFV infrastructure, and then that's all evolved to what we currently more commonly refer to as telco cloud. The characteristics and properties of that graphic, quite a bit of that we're going to kind of unpack in the rest of the talk, so I won't go into too much more detail there. The salient points, bullet points on the left are worth reflecting on. Firstly, the NFV and SDN kind of came with a big promise, and I think there was two parts to the big promise. Part one was lower TCO, lower total cost of ownership. If we move from vertically integrated vendor-specific stacks to a disaggregated model where we use a lot of commodity infrastructure, commodity compute and storage and networking, we're going to reduce costs. That was kind of part one of the big promise. Part two was always around flexibility and service agility. It kind of follows on from, if you disaggregate and break things down, you open things up and you enable flexibility and agility. We could probably reflect quite clearly that early deployments of NFV and SDN were probably a lot more about the what's rather than the hows. So moving to a model of using commodity compute and storage. In terms of actually leveraging a lot of the benefits of flexibility and agility, I think we are still on a journey towards that. I think the telco cloud as it is today, and then how it's going to evolve, and again, I'm going to dig into this more in the talk, is not something we saw in early deployments, but we're seeing much more now. And that's a good thing, because many of these promised benefits around agility and flexibility, they have benefits both for operators of networks and customers that rely on the services that run on those networks. And actually, I'm just, before getting into these 5 things that are driving the evolution, just going to say a little bit about what I'm calling BT's network cloud. So this is, if you like, BT's, what we call internally, our implementation of a telco cloud. And this is kind of a snapshot view of what this currently looks like. I do reference my colleagues, James and Curtis, who actually did a very detailed talk on this a few months ago. And as a reference in this slide to a nice talk they gave that goes into much more detail than I'm covering here. This is just to kind of help set the scene of telco cloud evolution. So what this thing called network cloud, 3 main things to know about this. The first one is So in terms of the cloud model, it's a private on-premise cloud infrastructure. Okay, so this is not reliant on public cloud hyperscalers. This is something BT have built and operate themselves. The second point is around the technology stack. It is, fully disaggregated. There are many open source components that make up this stack. Some of the icons on the top right of the slide illustrate that. One key point, for example, our virtualization software is from Canonical. Canonical are a UK-based software company. They also provide supported distribution of the Ubuntu operating system. So Ubuntu is kind of at the heart of this thing that we call BT Network Cloud. What actually runs on this, network cloud infrastructure? So for BT, we actually deliver both mobile and fixed services in the UK. This runs our mobile core. So we have softwareized mobile core that runs on this thing called Network Cloud. And this includes our 5G standalone, which Christian was talking about earlier in the introduction. We also use the Network Cloud to host an array of other functions. For example, in our fixed network space, one of the key components of our broadband service is authentication, something called Radius. That actually sits and runs on BT's Network Cloud. And there are a number of voice capabilities that also run on this platform. Just to quick indication of scale, in terms of the things that run on top, the tenants of the Network Cloud, the mobile services that BT operates in the UK, we use a brand name EE for that. I think we've got about 25 million subscribers, and a bit more than 10 million of those are 5G. In terms of broadband, we serve more than 9 million home broadband subscribers in the UK. So this thing is, at scale, and it's growing, and it will accommodate more tenants and services in the future. So, talking about the future, come to the main part of the talk, which is about, okay, what are the factors around how telco cloud is expected to evolve? I've got 5 things here, so I've called them 5 pillars. In some ways, the pillar thing can be a bit misleading because when you draw them like silos, it implies they don't touch each other, but actually there's quite a lot of overlap between these 5 things, okay? But it's just, convenient to represent them in this way. So get cloud native workloads and operations, hardware heterogeneity, the edge, energy efficiency, and secure computing. These are my 5 things that I think are important, kind of my opinion. You might be sitting there already and thinking, he's missed a couple. He's missed observability, and he's missed AI and automation. My get out clause on that one is observability and AI and automation absolutely do straddle right across the whole space. So I've not kind of described them as pillars in their own right, but they are kind of embedded capabilities and considerations across these 5 things. Okay, let's get into the 5 pillars one by one. I've also slightly cheated that my cloud native pillar is actually split into 2, so part 1 and part 2, and we'll see why shortly. But I break the cloud native story down into workloads and then operations and automation. So let's start with workloads. So what do I mean by workloads? Well, these are the services, applications, bits of software that are going to run on this telco cloud infrastructure. Why is cloud native important? Cloud native paradigms encompass a wide range of things. One of the key properties, if you like, of cloud native is the very modular implementation of software, and the breaking down software into very modular components. Often we talk about service-based architecture. That should absolutely lend itself to characteristics like portability, efficiency, visibility. Okay. Now let's just take those properties in a bit more detail. So we're looking at the key considerations part here. If we run softwareized network functions, let's call them, in modularized components that run in, for example, container runtimes, and they're orchestrated by container orchestrators. So this could be Docker and Kubernetes, for example. This should help us be more resource efficient than, for example, monolithic bits of software that run in virtual machines, for example. It should enable us to be more portable and performant. And this is kind of illustrated in the picture's a bit of an oversimplification, but hopefully it gets across the point. The portability bit is really saying, I don't want my software to be so, we sometimes use the term opinionated software, because it will only run in this container runtime orchestrated by this container orchestrator flavor, this underlying base operating system, and the hardware has to be this. That's not cloud native. So being cloud native is having that level of portability, and going hand in hand with the portability is I shouldn't then see a degradation in performance. So I should be able to have predictable performance as I move my workloads around. The last part of this is the visibility or observability piece. Metrics that I'm able to see from my software workloads through the stack should be consistent and, again, non-opinionated. I shouldn't have a situation where I only have access to a subset of metrics when I run software on a particular stack. I've used the word should deliberately on this part of the talk, mainly because all of those, it's a bit of a vision, that picture on the top right. Are we actually there yet? I would argue not quite, and there's work to do here. That is actually reflected by industry activity, where mainly telcos are kind of driving the industry towards telco vendors of telco softwareized network functions and workloads. To be truly cloud native, they have to meet certain criteria. And this is really what the CNTI Cloud Native Telecoms Initiative and the Linux Foundation, the NGMN published a thing called Cloud Native Manifesto. It's all kind of wrapped into that. It's not enough just to say we run in Kubernetes, therefore we're cloud native, because you might also say, but you cannot run on shared compute or be multi-tenant, or we need this amount of compute to guarantee performance. That's not truly cloud native. So it has to go beyond just running in Kubernetes and containers. Okay, now the little bubble at the bottom is just kind of hammering home that particular point. So the cloud native part one is about workloads. So the onus there is on vendors of softwareized network functions and applications that run on telco cloud. Part two of cloud native is getting into operations and automation. And this is the onus is now on the operator, because these are business practices in the world of cloud native and bringing them into the telco world. We could reflect that early implementations of NFV in terms of their approach to management and orchestration were pretty rigid and a bit inflexible. There's aspects of that, like being function-driven, imperative-based orchestration, i.e. being very prescriptive about how to do things and how to orchestrate virtual network functions onto underlying infrastructure. Early deployments pretty rigid in that sense. Where we've pivoted to in more recent times, and it's an onwards journey. We're not at the end state yet. There's a number of things that we're really kind of embracing here. This is listed under the key considerations, but platform oriented. So platform oriented, a simple way to think of that is a level of abstraction that the software can drop into to, again, we kind of address this issue of software being overly opinionated about what infrastructure it runs on. A platform-oriented approach can help address that and mitigate against that. It should also embody things like rich tooling and observability. But also, if we move to a model where the cloud infrastructure is not so centralized, but it becomes decentralized and distributed, a platform-oriented approach will lend itself to that. And I'm going to come back to the edge a little bit later. Intent-oriented, this is kind of the opposite of declarative versus imperative. You say what you want rather than how to go about doing it. Much of that is kind of enabled and facilitated by APIs. APIs enable a much more machine-to-machine interaction and take humans out of the equation. So reduce manual intervention, maximize automation. GitOps is an approach, a framework, very good for, I call it like one truth inventorization. The source is in one place. It gets modified, it gets updated, but at any point in time, there is a kind of one truth inventorization for software, data models, all that kind of thing. And the reason that's important, if you like, it's this thing about repeatability. Taking that approach and adopting those kind of models for managing cloudified infrastructure lends itself to repeatability and a unified way of doing things. So we can adopt very similar principles for life cycle management of centralized compute and adopt very similar principles for decentralized compute. The role of AI, we could think of it as AI ops. Now, the thing to say about that, two key points. First is it's kind of already there. The AI ops is adopted by telecoms operators such as BT, other operators doing similar things. Many things like root cause analysis, customer service, customer journeys, where they're interacting maybe with bots, chatbots, optimization lent to by data mining, big data analytics. It's kind of already there. But yeah, again, we're kind of at the start of an interesting journey. The second point I would say about AI ops, although this talk is about telco cloud, AI ops is not specific to telco cloud. It is telco full stop. So there's bits of telco that are absolutely not cloudified or disaggregated, but they can still leverage AI ops. Okay, and as I say at the bottom again, same point as for cloud native workloads, this is a work in progress. Okay, I'm going to change tack now. So talking a little bit about things like cloud native and workloads and operations, now getting down to the hardware layer and drilling into some interesting aspects of telco cloud evolution that we're seeing in this space. an interesting observation would be going back to the early days of things like NFV and SDN, where we were talking about disaggregation and commoditized compute and storage and so on. That principle was very geared towards avoiding any specialized hardware or acceleration. It was really trying to build a very kind of general purpose infrastructure that could be reused for many different things. And it's been pretty successful on the whole at doing that. But what's kind of happened in recent years, I would say, almost a bit of a pivot back towards, understanding that sometimes dedicated hardware that is complementary to the standard compute is not a bad thing. And in some cases, whether it's co-processors and GPUs or these offload cards called DPUs and IPUs, DPUs data processing unit, IPU infrastructure processing unit, other types of smart NICs, accelerators. The reason we're considering them is they are just more efficient at handling certain workloads than standard CPUs. The reason I think we're kind of coming full circle is just the range of possible applications and workloads and functions that it can make sense to run on a telco cloud infrastructure is wider than it was. And therefore, we want the benefits of disaggregation and flexibility, but we recognize that sometimes we might need certain hardware to do that particular job. What are the key considerations around that? There's a few things listed in the bottom left of the slide. First one is techno-economics. This is just another way of saying this would be, because you can do something doesn't mean you should do it. We know we could offload certain workloads to dedicated acceleration cards, maybe GPUs, maybe DPUs, IPUs, but there has to be a net techno-economic benefit of doing that. We have to convince ourselves that supporting that workload on pure standard compute just doesn't make techno-economic sense. We then get into considerations, interoperability and reuse. Although we're sort of hinting at, well, we use these cards for certain workloads, what we really don't want to do is almost have a special card for every specific special workload. What we would like is, although we recognize maybe certain cards are better than the CPUs, if we can use those cards for more than one thing that benefits from the acceleration, that's a better position to be in. Again, that kind of links back to the techno-economics. If we can get reuse of certain things, I've mentioned VRAN, virtual RAN in the radio space. There's some vendor capabilities out there already where dedicated accelerators are really good at doing baseband processing functions like forward error correction. But that's pretty much the only job they're good at. So that has to be balanced against the cost. If we have acceleration hardware that's able to do other things as well, that's a better story. So that portability and interop is a key thing. I've mentioned in the picture as well about management and operationalization. DPUs and IPUs, I set them apart from things like GPUs. They are architecturally very different and they're targeted at different applications and workloads. But another key point about DPUs and IPUs, they actually have their own self-contained operating system. And that operating system is independent of the operating system of the server, which is plugged in on a PCIe slot. Okay, so from a management point of view, there's a bit of a consideration comes in there on, I know I've got to life cycle manage my host server operating systems. Now I've also got to figure out how I do that for my DPUs and IPUs. AI impacts, whereas before I was sort of saying AI, it's maybe the realm of AI ops, where you're using AI to help manage your network maybe in an efficient way. Turning that on its head, the impact we could be thinking about here is AI workloads driving demand on telco cloud, and therefore using the right hardware to do that. I'll say a little bit more about that in the edge part, where I talk about LLMs and inferencing, agentic AI, all that kind of cool stuff that everyone's talking about. But just from a pure technology consideration point of view, it could be the reason GPUs are in this telco cloud space is because there are AI workloads themselves that it could make sense to host on that compute. The interesting angle on DPUs and IPUs, and it kind of adds a dimension to being cloud native, if you like, is the fact that they are programmable. They're programmable devices in terms of, you know, data management, data flows, all that kind of stuff. And there's a thing called the OPI, Open Programmable Interface project, where that's encouraging a kind of open ecosystem in the software suppliers and the hardware suppliers, and, you know, promoting as much interoperability as possible. Okay, this is the third of the 5 pillars, just about halfway through. Towards the edge, edge compute, like a few of these things we're talking about here, you could do a much more detailed talk just on this topic alone, and I think there's been past seminars that touch on edge in a lot more detail. But just, you know, a few kind of points from a telco operator perspective. First of all, even before getting into why is it important, one question I always frame at the start: where exactly is the edge? What do we mean by it? The edge can be, again, one of those loose terms, but, you know, there are some nice articles and definitions that get into a little bit of near edge, far edge, network edge, device edge, on-premise edge, and this whole notion of this thing called the compute continuum. A telco operator like BT, we have, you know, hundreds and thousands of exchanges in the hundreds of metro sites, as we call them, tens core sites, and then thousands of, we'll call them local exchange sites. Okay, we then end up, for our mobile network, we have greater than 10,000 sites where we have mobile infrastructure. So for us, when we talk about the edge as a telco operator, it really implies that we're going quite deep in the network. We could be at the metro edge, or we could be at that further exchange edge of the network. Why are there even considerations around going deeper? I always think there's 3 key points to this. The first of them is about efficiency. This is where the argument is around certain network capabilities, and in this case, the graphic on the right is talking about CDNs, content delivery networks, and where we put caches for services like Google, Netflix, Amazon, and so on and so forth. We put these in our network already, but potentially, because we have infrastructure at a very large number of places, we could go even deeper. The reason for doing that would be around traffic or capacity efficiency. When you put caches deeper in the network, what you're doing is you're turning around content much more locally to the end users, and that traffic then does not have to flow up and down at further parts of the network. So we can be much more efficient in how we plan the capacity that goes into our core network. That was actually a paper earlier in the year, and that's the NetSoft paper where I was hooking up with Christian, as we were talking about earlier. The second rationale, if you like, is performance. there's been talk for a very long time, I would say, in telecoms about the edge, and the reason to go to the edge is around latency sensitive applications, and they'll get a strong benefit by going deeper because you reduce the round trip times. It's all true to say that. Some of the applications like VR and AR have been knocking around in the 5G space for quite some time. vRAN would have some quite real-time networking considerations around latency, and certainly AI-related use cases. The thing to remember about the performance story is, for some networks, like in the UK, for example, we're talking about geographically a relatively small country compared to, for example, continental North America. The benefits you get by going deeper and deeper into the network in terms of latency kind of gets down to, you're talking maybe a millisecond by going maybe from core or metro locations to deeper on the network. That isn't necessarily going to buy you a lot of performance unless there is a super sensitivity to squeezing out that last millisecond. So yes, you can get performance benefits, but the argument for doing it might not always be that strong. The third point is often about data privacy and the fact that maybe we can intercept certain traffic types rather than going to a hyperscaler public cloud, we can process locally in a private telco cloud. The key considerations, it's again, because you can do it doesn't mean you should do it. So we need to think about the techno-economics. If you start building decentralized distributed compute, you have to understand how you manage both the compute and the workloads that run on top. In terms of AI, there's a lot of talk now when the edge gets talked about, it's AI and the edge and AI. That's fine to start thinking about that and talking about that. I would ask the question, is that still hype or how real is it? There's no doubt it's being hyped, but the reality, I think, has still got to be better understood. There are possibilities of hosting things like LLMs, the inferencing part of LLMs at the edge. There's possibilities to host things like agentic AI in the more decentralized part of that compute continuum framework. There's lots of industry activity around the edge. I've just mentioned a few things here, including some work in Europe from the European Commission. There's Linux Foundation Edge projects. I actually quickly checked this recently and I found there was 15 of these. Is that a good thing that there's 15 different projects all doing edge? I think it's down to the fact that there are very distinct use cases and verticals that make use of the edge, and that's why that feels a little bit fragmented. There is also under Linux Foundation something called Silva, and I think Silva is where there's more of an attempt to bring practices and principles for the edge in a much more unified way. Okay, energy efficiency. Why is this important? Well, when we operate our own private cloud infrastructure, we have a lot of servers, storage, networking. All of these things consume large amounts of power. There's kind of no getting away from that. The good news is there's quite a lot of tunability in compute infrastructure. The picture that I've got on the slide is kind of specific to Intel processors. So this is getting down to, one of the biggest things that consumes power on the server is the processor. Within the processor, there's things you can do to, tune the power consumption. C states are otherwise known as sleep states. If cores in a multi-core processor socket are not active at a point in time, they can go into various levels from shallow sleep states to quite deep sleep states. That's what's called C states. P states are active cores that can have their frequency settings changed. There's a thing called a base frequency on these processors, which is essentially the guaranteed frequency. There's then something called turbo frequency, which can be selectively burst above the base frequency. That's what's referred to as P states. Different frequency settings for cores will result in different levels of power consumption. There's then something called uncore frequency. Uncore is the part of the processor die that doesn't have the cores on them. This is a kind of Intel term. So things like high-speed interconnect, last level cache, the power control unit itself, these are kind of embedded on this part of the processor socket called the uncore. And actually, it itself has a tunable frequency setting. So you can tune the frequency up and down, you will get different levels of power consumption. Now, we could think just quite simplistically of, well, let's go and set everything to be as power efficient as we possibly can. The first key consideration in this space is usually modifying the power setting will have some kind of impact on the performance of the workloads that are running on this compute. So we have to be very mindful, especially in a telco cloud context, where we get mobile core, broadband components that rely on these capabilities, that we don't just tune down all the power consumption and then we might see issues with performance. That in itself is facilitated a lot by observability. The more data metrics we have telling us about performance and resource consumption on the one hand and corresponding power consumption, that helps us achieve a balance between the two things. We can get quite sophisticated in this space. That paper that I've pointed out there, that's not a BT one, by the way, that's just in the public domain. But it gets into using AI in terms of reinforcement learning to have a very sort of adaptive and continuous approach to tuning server optimization. So that's a kind of sophisticated approach we can take. There are other things we can do, though. There are certain power settings on servers that can potentially give, I call them quick wins. They're fairly simplistic. They don't all necessarily have a direct impact on performance. And therefore, we get that quick win effect. The example shown there is just something in Network Cloud that was done recently, and it resulted in, it was a particular server setting which changed. It resulted in a 10 kilowatt drop across that particular site. Didn't require anything more than a config change. I'm going to skip over this slide, but it's there. Basically what this is, it's a little bit of a promo for BT and Intel research. Over the last few years, we've jointly published research around some of those things I alluded to in the previous slide around Intel processors and what can be tuned to have an effect on power consumption, but at the same time factoring in performance. We've looked at turbo frequency, we've looked at memory bandwidth throttling, we've looked at uncore frequency tuning, and we've looked at deliberately kind of going single socket, cross socket for different workloads and seeing what effect that has. These are all just sort of references from recent conferences where we've jointly published on that. So that's just really there for further interest. I'm going to come to the last pillar and then wrap up because I'm conscious also of the time. Should be done in 5 minutes or so. The last of these 5 things is secure compute. So before even thinking about security and secure computing, this cloudified infrastructure, because this, so for example, I've talked about BT's Network Cloud, that's our implementation of this thing called Telco Cloud. It hosts mobile core network, key components of fixed broadband. That is deemed to be, from a kind of governmental point of view, that's critical network infrastructure, CNI for short. Now, when you have CNI, critical network infrastructure, by definition, security is absolutely paramount. There are a whole raft of security best practices and principles that are baked into the cloud infrastructure. That has not been the point of this talk, but what we're doing is we're signposting. So from an evolution point of view, what are some things in secure computing that could land into the telco cloud space in the future? The first of two things, and I just touched on these quite lightly, something called CHERI. CHERI is an acronym. It's said at the bottom of the slide: Capability Hardware Enhanced Risk Instructions. This was born out of Cambridge University in the UK. CHERI is an alternative processor architecture where the instruction set incorporates certain ways of dealing with memory management. And the whole purpose of this is to mitigate against a very specific type of vulnerability, which is memory safety. There are ways of dealing with memory safety in the software world. There are some programming languages that are, memory safe, others that aren't. What this is doing is addressing memory safety at the, if you like, the hardware or the processor level. BT joined this thing called the CHERI Alliance early this year. We see this as a kind of important direction for the future. The second thing is around trust and attestation. Attestation in this context is around booting up software on hardware and being able to attest, we sort of call it the provenance of that software. If the software boots to a known configuration, we can say it's not been tampered with. If it's not to a known configuration, it would suggest that it's been tampered with. Now, the ability to prove and attest the software booting on cloud compute infrastructure is actually something that's kind of going to be mandated, a legal requirement in the UK in coming years. We have a thing called the Telecoms Security Act, and then as part of that, a thing called the Telecoms Security Code of Practice. And baked into that are very specific requirements around attestation and being able to show and demonstrate how we do that on cloud infrastructure. So that's another way of secure computing and how that's going to drive the evolution of telco cloud. Just to wrap up, I think the sort of point I try and make on this slide here, so I think two main points. There's this sort of inflection point from the very early days of NFV and SDN to where we are today with kind of telco cloud and a bit of a work in progress towards cloud native. And that is a work in progress. And I would say the principles of cloud native have been adopted gradually. There's then this AI impact and becoming, well, if you're AI ready, AI native. What that really means, I think, is still being addressed across industry. I know there was another one of these seminars that went into AI native. I think the thing I would reflect on this is, while it seems pretty obvious that this is the next thing that will have a huge impact on telco cloud, in a similar way to cloud native was not big bang. It kind of, we evolved from a starting point and we've not got to the end state yet and we're still evolving. I think that's probably going to be a similar thing we see with AI ready and AI native, because already there are things creeping in terms of AI ops on the one hand and maybe running certain workloads that you could deem to be AI on telco cloud. Okay. And there's a white paper we wrote, me and a couple of colleagues earlier in the year, which actually some of the content of this talk is kind of linked to that white paper. It's public domain. I've included the link at the end here. So anyone's free to go and download that should they wish. I'll stop there because we definitely wanted to make sure there was 10 minutes at the end for questions.
Yes.
I'll hand back to yourself, Christian. I think I've stopped sharing, or do I need to stop share? Yeah, stop sharing.
Great. Thank you. Thank you very much, Paul. That was great insights. And now it's the part where I was going through some of the questions from our students, and I selected 3 of them. There are over 40. I will share with them. They have done their homework, so I'm very happy with this season. The students are really doing a great job, despite the challenge, because they are not all networking cloudy students. I will start with an easy one, because you mentioned AI several times, but in a generic way. I would like to ask you, and also from a personal perspective, if you can share one example where you have recently seen AI in some network automation demonstrator or feature that has surprised you, that you would like to highlight. Please share with us.
Yeah, I think I probably just linking back to one of the examples, I glossed over it quite quickly earlier. In terms of power management, so power management of standard servers, you have a lot of you've got a lot of things that can be tuned, a lot of things that can be configured. You have a lot of telemetry and resource metrics that can tell you what your current state of resource consumption is at any point in time. Now, you can try and do that manually. You can try and automate it with basic approaches to automation, like scripting and so on. What we've actually seen, though, is this is an area that absolutely lends itself to, I would say, the flavour of AI, and actually referenced one of the interesting papers on this, was using reinforcement learning. So reinforcement learning for this kind of problem, where there's a constant cause effect, the tuning, the observation phase on what is that doing to my power, what is that doing to performance based on certain metrics. That particular dynamic tuning of power consumption whilst balancing against performance absolutely lends itself to that particular flavour of AI. There might be other AI flavours that are similar or can do as good a job, but RL definitely, we've seen that. We've seen it in other places. It's something kind of exploring for ourselves as well. Is it embedded in production environments? I would say that's not necessarily part of our existing setup. Part of what we do in research is understand the implications of doing those kind of things, and then they get adopted into our production networks.
Right.
What we kind of do is feel our way into these things and understand if there's maybe quick wins to apply first, and then we get into the more sophisticated way of doing things. One of the reasons it's a challenge, I would say, is if you're doing some kind of machine learning, like reinforcement learning, if you introduce that into production environment, you then have to understand how you're going to maintain it, how you're going to feed and water it, and that's like ML ops, isn't it? So you need to look after that model, how it's been trained, how it's been updated. Has the state of the network changed significantly that it now needs to be updated? So it's pretty non-trivial, I'll be honest. This goes with a whole operational surround that we're still feeling our way into.
Yeah, the never-ending model drift, the explainability as well. These are hard challenges. Some of the students ask already whether in the energy efficiency you are accounting even for the energy that the AI is consuming for providing the efficiency gains. But
that's a great point. That's why I always go on about techno-economic benefits, because you have to almost, it's like a whole life total cost of ownership. Yes, you've saved money down here, but over here you're burning really hot. So
you have just shifted. And talking about shifts, I think this question was also very, very smart. Let's see if it resonates to you. The evolution of telecom architectures seems cyclical. We move from integrated hardware to desegregation over NFV to gain flexibility, and now we are getting back to specialized hardware through the DPUs, the smart NICs, and all this to improve performance. And if operators start doing these accelerators, adopting these hardware accelerators that you also mentioned, would that not recreate again a vendor lock-in, but another vendor, and then bring rigidity in our stack that NFV was designed to eliminate? How are you seeing this? Do you agree? What's your view?
I really like that question. It's spot on. It's absolutely accurate. So I was talked about quite quickly in the part about hardware heterogeneity, and we have seen this flip flop of standard compute, no specialized hardware, to let's use specialized hardware, and there then comes with it the risk of vendor lock-in. What I was saying earlier was we have to absolutely make sure that whatever these devices are, that they are not just single purpose. So they have to be usable for more than one thing. Now, that in itself is probably not enough, because if they can be used by more than one thing, but they're only from the same software vendor, for example, then that's still not very good. So there needs to be maximum kind of portability between the hardware itself and the ISVs, as we call them, the software vendors on top. I mentioned things like the OPI project, and that has the intention of ensuring that there is a bit of openness and there's not too much lock-in and vertical integration. What I would say is, in reality, these industry bodies are great, but what we often have to do is really work as a telco. We have to work with the vendors of those DPUs and IPUs, and we have to work with the vendors of the software, and we have to kind of give them reasons for and encourage them to kind of maximize their portability and support across different underlying hardware platforms. What we often hear back from, for example, software vendors, and it's understandable and it's true, for every flavor of different hardware that they have to test against and validate and certify, that's a burden on them, right? so we understand that that's a cost of ownership problem for them. So I think there's always got to be a sweet spot for us as a telco, the hardware vendor, the software vendors, that we have enough flexibility and enough choice. But maybe there's a limit to how much flexibility and choice we need. We don't want 100 versions of things, but we want to be able to have a choice. So I think there's a spot balance somewhere, but it was a spot on question. It's absolutely something to think about.
Thanks, Paul. And I think you answered already this other one that I had also selected as the third one, but we are already 2 p.m. in Brazil time. Our students need to join their afternoon classes. I use this lunch slot for running these seminars. So thank you very, very much. Next week, we'll have another interesting one that I hope everyone will join. Paul, looking forward to meeting you again in person and interacting. And
Definitely,
thank you, everyone.
Christian. Yeah, no, I really enjoyed it, and have a good rest of the day to you. And you have some very good students.
I will share the slides with you, their homework. Okay, thank you. Take care. Bye bye.
Thanks, everyone. Bye.